Hello everyone. Today I will present my CS584 project, graph mining project. My project topic is beyond homophony in representation learning for attributed multiplex heterogeneous network. So first, what is beyond homophony? So homophony is a key principle of many real-world networks, whereby linked nodes often belong to the same class or have similar features. As the old saying says, birds of a feather flock together. However, why we need to consider beyond homophony? So we define the low homophony as heterophony. So what is heterophony? Heterophony means linked nodes are likely to from different classes or have dissimilar features. In real-world cases, this could happen. For example, in biology, in protein structures, different amino acid types are likely to connect to each other. So not the same nodes connected to each other, but the different nodes connected to each other. So under these scenarios, we need to consider the heterophony. So to consider the heterophony, we first need to have some notation and preliminaries. As defined in a 2020 paper, the author defined the age homophony ratio to reflect the homophony and heterophony in homogeneous networks. So what is the homogeneous networks? Homogeneous means in these networks, there's only one type of load and one type of age. It's a simple graph to study. And homogeneous is different from homophony. It focuses on the types and ages. And homophony is another principle. Okay, so we focus on the homophony and we define the homophony ratio here. And as the definition of the homophony ratio, it is a fraction of ages in a graph which collected loads have the same class label. By the definition, you can see graphs with stronger homophony will have a higher age homophony ratio, close to 1, and graphs with stronger heterophony, which is no homophony, will have smaller age homophony ratio, close to 0. So the author also studied in the homogeneous networks how we learn when the graph is on the heterophony. So first let us review the definition of graph neural networks. So such as graph convolutional networks. The basic idea of graph neural networks is to learn the embedding of a load based on its own features, own embedding at each round with the embedding from its labels. So it applies an aggregator function on its own feature and the feature of its labels. So for graph convolutional networks model, it's just averaging the features of its own and its labels. On the homophony, it causes no problem because the assumption is that the node is similar to the labels. But on the heterophony, it will cause problem because you need to distinguish the load with its labels because they are different. So there are many designs to learn the representation on the heterophony in homogeneous networks. And the author in 2020 paper classified them to 3 categories. So the 3 categories are: first, the design 1 in the aggregator function f is to distinguish ego and label embedding separations, which means rather than averaging the ego and label embeddings as the GCN do, the model would use a explicit aggregator function to distinguish the 2 embeddings. This is proposed by the model graph Sage. And the second design is higher order labels, which means to learn under the heterophony, we need to consider higher order labels because the load is different from its labels, but it could be the same from its label from at the 2 hoop. So at the second hoop. So the second design is to consider higher order label hoops, like the model mixed hoop did. And the third design is a combination of intermediate representations because we have k rounds of the graph convolutional layers. So each round will have different, will have the information at different levels. Under heterophony, each of the information could be useful for learning the embedding. So the third design is to not to combine all the intermediate representations. So just to mention, just to remind you that GCN just keep the last round in representations. So and then these designs, three designs are proposed to learn the representation in homogeneous networks. But in our study, we want to learn the representation in heterogeneous networks. So what is a heterogeneous network? So heterogeneous network is more complex and more prevalent in our daily life. It means in these networks, there are multiple types of loads and multiple types of edges. And the attributed multiplex heterogeneous networks means that the loads have attributes like features, and the edges are multi-typed, which can be divided to multiple sub-views of the network. So many current researchers have been doing the multi-view structure of the heterogeneous networks, such as this graph. It shows it is from a recent paper, and it shows in the e-commercial data set the networks could be modeled in a multi-view architecture into different views, and in each view the information is complementary and could be used to learn the representation of the loads. However, the problem in this learning process is that the current models didn't consider the heterophony in each subview. As we mentioned, even in a simple homogeneous network, it could be under heterophony. In this complex multi-view architecture of heterogeneous networks, heterophony could be more often occurs more often. And so in our project, we want to apply the designs in these sub-networks. So this sub-networks is homogeneous with only one edge type. So it's easy to apply the existing designs of aggregators to the sub-networks, homogeneous sub-networks. So for the problem formulation of the attributed multiplex heterogeneous networks, we show the definition here. It's a network H with different types of loads V and different type of edges E, and for certain edge R, we can represent the heterogeneous network into different subviews and subnetworks, and in each subnetwork is information networks with the homogeneous edge type. In each view, we only have one edge type. It will facilitate the learning of representations. And the proposed method to start with, our proposed method is just a modification of current, not a modification, it's an improvement on our current representation learning network methods on the heterogeneous networks. So the main difference here, so this, generally speaking, this algorithms, the aim of this algorithm is to use the information of different views for the representation learning. And the main improvement here is for the subviews. For learning the representation of subviews, we apply the designs in the aggregator functions to distinguish the subviews with homophony and subviews with heterophony. So for the current experiment, we investigated two data sets of two homogeneous data set. Why we use the homogeneous data set in our current results? Because we first need to understand which of the design would help more on, and have to what extent the homophony or heterophony need different designs of the aggregated function. So to start with, we use two homogeneous data set, Texas and Cora. Texas is web pages of University of Texas, and those are web pages, and the edges are the links, whether pages are cited are linked to other pages. And Cora is the machine learning papers, and it's a well-known benchmark. And the loads are the papers, and the edges are whether a paper cited another paper, and they have different homophony ratio. So Texas homophony ratio is very low, which means it's under heterophony, and Cora homophony ratio is high, which means it's under homophony. Texas is under heterophony. And for the models, we use so the baseline design of the aggregated function, we use GCN. And for the design of D1, which means separate the equal and label embeddings, we use graph-sig with different aggregators. And for the second design, we use mixed hoop to consider the higher order labels. And for third design, we use the jumping knowledge networks to consider intermediate representations. And and we also consider the model proposed by in 2020, which like combines all the three designs. And because it combines all the three designs under whatever homophony ratios, it should be able to learn the representation. It is capable to learn the representation. And the result is summarized in the table. For these two data sets, we can see that design 2, design 3, and combining all the design improve the classification accuracy on the Texas data set, which is under the heterophony. And the first design here, the graph-sig didn't improve its classification accuracy. It is contradictory to the original John Drew's paper in 2020, because they say that all three designs improve the learning, both theoretically and in practice, and in real data sets. I think it's because we use the different graph-sig variants. I didn't use the graph-sig LSTM in these experiments, but they didn't mention whether they use graph-sig LSTM or graph-sig GCN. But I think that could be the reason why I didn't have like a higher accuracy using graph-sig. But for Cora, the homophony, the data under homophony, all the models have like a similar. All the models have a similar classification accuracy. So the result shows that the designs in the aggregated function could improve the representation learning accuracy on the homogeneous data networks under heterophony. So the next step is to apply these aggregated functions in the heterogeneous networks. Okay, it's very like so heterogeneous networks with homophony or heterophony, which means the subview or subnetworks of the heterogeneous networks, when it's under heterophony, we should use the proper aggregated functions to learn the representation. And in our results, we can see if we combine like what the H2 GCN do, if we combine all the three designs, it could learn the representation both under heterophony and homophony. So we don't need to distinguish the homophony and heterophony in each subview, but but we can just combine all the designs on these subviews to improve the representation learning performance on the heterogeneous network. That's I'm going to do in the following work to choose the data sets and to apply the models. So for the takeaway message, so the takeaway message of my current results is that first, beyond homophony, which means homophony is not always the boss, heterophony could exist in real-world networks, and it is important to consider the phenomenon of heterophony. And second, is design of the aggregate functions based on the structure and the content of graph could help learn the representation when it's under heterophony or homophony. So the aggregate functions is important. Thank you.